Hello, my name is Emmanuel, and my CS 109 challenge project is titled Probabilistic Modeling of Balloon Landing Locations for the Stanford Student Space Initiative. Some really brief context, I'm part of the SSI Balloons team, and this is us doing a balloons launch near Santa Cruz earlier this quarter. Attached to the balloon you see in this picture is a payload, and for both logistics, like hotels, etc., and also payload recovery purposes, it's really helpful for us to know approximately where the balloon is going to land before we even launch it. So this requires trajectory and landing location prediction. Most amateur balloon launchers will use this website out of SonTub to do the prediction. And what it does is you pass in a input launch location, in this case near Cowell, and also some parameters related to your balloon. And then it returns to you the trajectory in black, and also a output landing location in this green point here. So I took a look at this and I thought it would be much more informative if instead of a single location being output, it would actually output the entire probability distribution over which we think the balloon will land. So my CS109 project is implementing this function by both computing and then visualizing the probability distribution for balloon landing location. As a disclaimer, the rest of this video is going to dive into the math and the probability concepts that I'm going to use. And it's going to be a bit on the long side because there's 4 distinct concepts that go into solving this problem. But it's also in the write-up, so if you prefer just to read that, feel free to do so. Okay, so the core idea behind the visualization and the computation is instead of simulating a single trajectory, we're actually going to simulate 441 separate trajectories and landing points. You can imagine that on the back end, what's happening is that for each trajectory you simulate, you're calling a function called simulate. And you're going to pass into this function a set of parameters. For example, the launch location, but also say the balloon ascent rate and other factors. Now let's imagine instead of launching at this specific location here in this coordinate lat long, we actually launched at a slightly different location the day of because the terrain was not exactly what we expected when we got there. In that case, we can model the new coordinates as the initial coordinate plus some deviation. And this deviation can be expressed in a variety of ways. Here I'm just going to use random.uniform and choose appropriate values. So 0.001 degrees in either direction, let's say. And when we pass in these new parameters to the simulate function, it's going to output a slightly different trajectory and landing location. And you can imagine passing in varying sets of input parameters to get a whole range of different landing points. And this will be the data source for our probability distribution that we're going to try and visualize. So the concept behind this is called Monte Carlo. And it's really powerful and also really cool. So if you have time, I highly recommend looking on Wikipedia to get a better understanding. The next challenge then is to actually convert this set of 441 landing points into a probability distribution. And before I dive into the actual implementation, I kind of wanted to provide some intuition. So first, imagine that your 441 points all cluster into this tiny region, or a relatively small region. In that case, you want your 3D probability distribution to have a spike or bump above that region in which they're clustered. And so that's what I'm trying to draw here in blue. Excuse my terrible 3D drawing. On the opposite end of things, if your landing locations are instead distributed pretty evenly among the area, then you want your probability distribution to reflect that as well. And so it should be relatively flat over that area. And so this is like a uniform distribution, but in 3D, essentially. Now let's take a closer look at the implementation by just examining a case in which we have 2 landing points, and we're trying to calculate the probability distribution over this bounded black region, given just these points. And so the core idea is we're going to actually assign a probability mass kernel to each of these points. So this is the kernel for the leftmost point, this blue thing that I'm tracing, and this is the kernel for the rightmost point, the other blue thing that I'm tracing. And this kernel is essentially a Gaussian, but rotated about its center. So it's like a 3D Gaussian, essentially. And there's other choices you can make for the shape of this, but I just chose a Gaussian because it's most familiar given 109. So to actually see how this works, let's just start choosing points from this region. Let's say we're trying to model the probability that the balloon's going to land at this purple point, and we're going to draw the probability axis, vertically. How we do this is we sum the contribution from each of the kernels. So the contribution from the left kernel here is close to 0 because as you go further away from the center of the kernel height drops off. And the kernel contribution from the right kernel is even smaller because it's even further away from the purple point. So 0 plus 0 is 0, so we're going to draw an X where the 0 line is on the probability axis. Let's take another point. Let's say we're trying to find the probability that the balloon lands here. Well, in this case, the left kernel contributes this much probability mass, you could say, whereas the right kernel contributes a lot less because it drops off really quickly as you go further away from it, but maybe still a little bit, so something like this. And finally, let's take a kernel right between the 2 landing points that we got. In that case, each kernel contributes equally about this much. So if we sum those 2, we get a point here. So now we have a way of computing the probability of a balloon landing at each point inside this bounded black region. And if we can combine and draw or shade the regions that connect all these x's, we get something that will probably look like this. And this is exactly what we wanted to do in our intuitive kind of reasoning examples. To actually implement this in our case of balloon landing location modeling, we need to divide the landing location into grid cells because we can't afford to compute a bajillion purple points. So imagine that all the landing locations are inside this box. Then we can divide the box into grid cells and compute the probability of a balloon landing in the center of the grid cell instead of at every single point. And so the algorithm to do that is here. For each cell in the grid, first we're going to calculate the kernel weight at that point in the grid. So it's going to be a function of the distance here. We're going to sum all the kernel weights from all the kernels. And then that sum, which is encapsulated by this variable density, is going to be assigned to that grid cell. So you can imagine that the output of this is going to be a grid of landing location, and each cell in that grid has a particular probability mass corresponding to how likely the landing is going to be in that cell. So we can just arbitrarily fill this in, say, with 170, 20, 50, etc. And so this technique is called kernel density estimation, or KDE for short. And it's also really interesting and really cool. So also highly recommend reading about. The next challenge then is to actually visualize the probability distribution that we computed. So you imagine that we have now this grid on a map, and inside each grid cell is a value that says approximately what's the likelihood of a balloon landing in that cell. But imagine if I were to tell you that there's a 2.1% chance that a balloon is going to land in this 10 by 10 meter cell or something like that. This is actually not very helpful because it's a tiny region and also tiny probability, and that doesn't really help you see anything about the launch itself when you zoom out and think of logistics and planning purposes. So now you might be thinking, this is exactly why we have the cumulative density function, right? Because we want to actually shade all the cells that contribute to, say, 50% probability of the balloon landing in that region. The problem is that if we were to take a look at this grid, the sample grid, and let's just say that we're trying to shade exactly 120 mass units, there's multiple ways to do this. So for example, you can shade 100, 10, and 10, but you can also shade 40 and 80, or even 50 and 70. And this is a problem because we don't want to be returning the user multiple answers or multiple cumulative density regions in which the masses in that region sum to 50% of the total mass, for example. So instead, we're actually going to use a concept called highest density regions, or HDRs. And the core idea behind, say, the 50% HDR is we still want 50% of the mass to be in the HDR, but we actually want to choose the fewest number of cells to make that happen. So let's explain this by going through an example. We have the same probability grid as with the CDF, and the total mass is just summing the values in all the cells, and we get 530. So for the 50% HDR, we want to have more than 265 of the mass units in our selected region. And the way to do this using the fewest number of cells is just to take the highest value cells, in this case, 190 and 80. And we see that sums to 270, which is greater than 265. So our 50% HDR in this case would be these three cells. And unlike with the CDF, this is actually unique. So this is a very powerful property of HDRs that we're going to exploit. So the core concept here is HDRs. Now onto the home stretch, we have the grid of landing locations, and we have the probability of a balloon landing in each cell in the grid. And we know which cells we want to highlight for the user. How do we actually highlight them? Well, the first thing you think of is probably just to directly highlight those cells. But then we run into the same problem of if these cells happen to be discontinuous, so for example, something like this, then it's kind of ugly to look at and also doesn't really help for you to say there's a 2.1% chance that the balloon's going to land in this tiny cell. Same problem as before. So instead, we're actually going to employ an algorithm called the convex hull algorithm. And what the convex hull algorithm does is it draws the smallest convex polygon that it can around the cells that need to be highlighted. So in this case, the convex hull algorithm would return this, and it would shade this region. So this is a great approximation for the area that you want. And you can note that it kind of overshoots because there's this region in the middle here that is not something we want to highlight, but is covered anyways. But if you were to actually zoom out and in the grand scheme of things, this would be a very small amount of the total region. So it's an approximation, but it works pretty well. So the convex hull algorithm, the specific implementation that I use in the code is called gram scan. And it's really, really cool. It basically rotates lines clockwise and counterclockwise to find the convex polygon. And I'd also recommend checking this one out. So putting this all together, we know how we can calculate the X% HDR given our grid of values that we generate using KDE. And so we can do this for 30% and 50% and 70% and just any probability percentage that we want. And this is exactly what our function does. All right, now let's test this function by calling it off the roof of Hewlett. The main downside is that the function does take longer to run because you're loading in many different weather models for the Monte Carlo part of the simulation. However, hopefully it's worth it because now you can actually quantify the uncertainty. Thank you for watching.